Hi guys, welcome back. Let's talk about publication bias. So publication bias is when the likelihood of publication depends on the nature and direction of results. Significant effects are more likely to be published, and fundamentally that's been the nature of the game for a long time, where and it's driven a lot of research in very poor directions, and confusing directions as well. Type 1 publication errors are underestimated to an extent that is frightening, even calling into question the scientific basis for much published literature. I'll tell you now, there's a lot of literature out there, and I don't want to be too skeptical, but you should be critical of what you read, because I think students in particular, when they read papers, they think that the paper itself, for it to be published, is a high standard. And that's true. It goes through peer review. Some journals have a much more rigorous peer review system than others, in the sense that the reviewers are better selected, better expertise in relevant domain and matched, and provide better feedback. But fundamentally, people can be driven by, is there a finding here or not? I'll tell you a story to emphasize this point. I had a colleague of mine who was conducting a study, and the purpose of the study was to show that there was no difference in the areas between two different brain regions. And so one brain region could be used as a reference point, and another as well, because there's no difference between them. And so he did the study, found that there was no difference, as he had expected, and he tried to publish it. And he ended up trying with 7 different top tier journals, and eventually got it published. And that's not unheard of. It does take time to publish different journals for different reasons, but that was the hardest paper he had to publish, and that was because it didn't have a statistically significant finding. The finding was that there was no finding, and so it can be challenging to publish papers that have no finding. Now, this is changing. The guard is changing, certainly, as time goes on, and people are more aware of this and the need to publish non-significant findings. But in any case, it's definitely been taken to the extreme over the years in terms of how we think about publication, and leads to a bias in what we see. So the extreme view of the file drawer problem is that journals are filled with 5% of the studies that show type 1 errors, while the file drawers are filled with 95% of the studies that show non-significant results. So if you understand the type 1 errors now, then you get a sense of what this comment means, and the fact that when you have a type 1 error, you detect the effect when really you shouldn't be detecting effects. The null hypothesis should be you should fail to reject it, but you do reject it because you've created a type 1 error, and that gets published. And the file drawer is filled with all these studies that actually show non-significant results, because the true effect is that there's no difference. There's no effect in the null hypothesis. So that's really the file drawer problem. I know an old analogy. I'm not sure how many people put documents in their file drawer now with their papers. I mean, maybe there's some, but it shows how long this has been going on for. This is in 1979 that this was highlighted and written. So there's a tendency for non-significant results to be filed away or hidden and not published. Number of null studies which would have to be filed away in order for a body of significant publishing effects to be considered doubtful. So if there's 1 or 2 studies that show a significant effect, then sometimes there's many people who see an effect, who replicate part of the study and find no effect, think that what they've done is maybe incorrect, where in fact many other people may be doing the same thing, storing it away in file drawers and not publishing. And that attitude's changing over time, but it's an issue. So there's 2 counteracting biases. One is low power, so underestimation of real effects, and publication bias, or file drawer effect, which is overestimation of real effects, right? So the real effects are published, and those that are real effects are published, and those that don't show an effect are put in the file drawer. So funnel plots, we have statistical tools to help us with navigating this visually. So funnel plots are a scatter plot of treatment effect against study size. It's a precision in estimating the true treatment effect increases as sample size increases. So studies with small sample sizes scatter more widely at the bottom of the graph, which is less precision, and those with larger sample sizes are at the top of the graph. So, and I'll show you a funnel plot in a moment. So in the absence of publication bias, the plot should resemble a symmetric inverted funnel. So here's the example of a funnel plot. So on the left are measures from my systematic review that was looking at different measures of cholesterol changes in women pre and post menopause. And on the right, you can see that this is called the trim and fill method. So what this does is it takes away studies that may be overly influential and fills with studies that they think would be there had they been published. So it allows for a sense of trying to rejig the plot so that it's more balanced to represent what would it look like had all publications be published in this topic. And you can see that as they are the sample size, so size with small sample size scatter more widely at the bottom of the graph. So if they're at the bottom, they probably have low sample sizes, and up the top they have large sample sizes. And standard error decreases as sample size increases, right? So the standard, as your sample size increase, your standard error decreases, so you have more precision. So that's what we see here. And you can see the filled in the white dots here. So this is an example of a trim and fill plot, and you'll see a lot of them in systematic reviews, and really it's trying to address this publication bias question. So if there is publication bias, this will cause meta-analyses to overestimate effects, right? So if there are only studies that are publishing when they detect effects, and those that don't detect effects are not published then, or not able to be published, then this can influence the effects that are seen in meta-analyses. So meta-analyses is where it's an aggregation of studies, right? So say you may have heard commonly that, say, red wine is not good for you or red wine is good for you. I mean, this is largely attributable to science communication about the topic. But if we did a meta-analysis, this would aggregate all studies in relation to this topic, and then it would see what's the overall effect that we see. So in that trunk fat percentage example, that was a meta-analysis where I was looking at fat mass between pre and postmenopausal women, looking at all studies that looked at the differences and getting an average effect. So what I found was that there was the average effect was 5.49% increase between pre and postmenopausal women in trunk fat. So there's greater deposition of fat essentially. So the more pronounced the funnel plot asymmetry, the more likely it is that the amount of bias will be substantial. Now, what are the ways we can counteract the bias? Well, there are some journals out there, Journal of Articles in Support of the Null Hypothesis or Journal of Negative Results. There are journals that are very supportive of people publishing their findings, regardless of what their findings show. There's even some journals that encourage people to publish their methodology and how they're going to do the study, and then they conduct it, then it's reviewed thoroughly, and then once it's reviewed and accepted, the authors will conduct the study. Regardless of what the results are, that paper can get published as in addition to what they had there previously. So it really puts the emphasis on, we want to critically analyze the methodology and interpretation of findings, but ensure that the process of conducting the research is transparent in science. So, summary of publication bias: tendency for statistically significant studies to be published over non-significant studies, indicated by a gap in the funnel plot or file drawer effect. Counteracting biases in scientific publishing is there's a tendency towards low power studies which underestimate effects, to publish significant effects over non-significant effects. We need to counteract these biases, and that's done through many journals. So let's talk a bit about academic integrity. Academic integrity, often in university contexts, is students may think it applies just for students, but it applies for academics as well. And Richard Horton wrote this paper. He was the editor of The Lancet, which is one of the world's oldest and best known medical journals, who wrote this article saying that a lot of what is published is incorrect. Much of the scientific literature, perhaps half, may simply be untrue, afflicted by studies with small sample sizes, tiny effects, invalid exploratory analyses, and flagrant conflict of interest, together with an obsession for pursuing fashionable trends of dubious importance. Scientists too often sculpt data to fit their preferred theory of the world, or they retrofit hypotheses to fit their data. Our love of significance pollutes the literature with many a statistical fairy tale. And I honestly couldn't agree more. And it's one, if you ever consider doing further research beyond this course, I hope that this course has set you up with the ethics and integrity and transparency to be able to be a good researcher, be a researcher who tries to do their best to make sense of the data, to follow the scientific method, to follow the principles of transparency and openness and discourse that allows us to actually push the needle forward in science rather than muddy the waters through the ways that it has been gamified in some ways. And so I think it's really, really important. And there are people watching and paying attention, and it can cause significant reputational damage if it's done poorly. For example, Retraction Watch is something where you can sign up for their emails, and they tell you all the papers that are being retracted each day. So authors have papers in Nature and Science retracted on the same day. That's an article there. This was due to fabrication of data. The Science paper was cited 240 times, and the Nature paper had been cited 119 times. In my research field in Alzheimer's disease, there was again a similar case of fabricated data which lend support to the amyloid hypothesis, which is a hypothesis that amyloid is a protein that is really the cause of Alzheimer's disease. And there are these other changes that we see in the brain, like tau the tau tangles can occur, these tangles in the cell, but people have pushed that aside for many years because of all this evidence about amyloid. And in the last few years, or in several years, they found that, in fact, some of the seminal research was actually fraudulent. And this doesn't mean it discredits everything about amyloid, but it does mean that significant advances, like when all these drug medications that were targeting amyloids and seeing no results in human studies, we were wondering why, and really it shows how much it can push back the timeline for our ability to advance a field of research. And so it happens for many reasons. Academics feel pressured to publish or perish. You may have heard that phrase. And publishing sometimes means focusing on results that are statistically significant. But again, this is why this whole culture is really important to change. And it starts, I think, individually with people holding themselves to high levels of ethics in science and realizing that their research and their work matters and the implications that has. And that's why, again, science communication is very important, something I'm passionate about. So summary of academic integrity: violations of academic integrity are most prevalent amongst those with incentives to cheat. For example, it can happen with students, of course, as well as academics, but competitively funded researchers and commercially sponsored researchers. So you want to adapt a balanced, critical approach, striving for objectivity and academic integrity. So it's very, very important, particularly in the research context. So what are some solutions? I've painted a dire picture of fraudulent research, of all these issues that occur in misrepresenting findings. How do we solve this? Well, hopefully you get a sense of some of those tricks, but one is using open science at each stage of the research process. So record your study design, data collection methods, including sample size, data exclusion rules, and analysis to reduce biases associated with cherry picking or capitalizing on chance. So I think pre-registered studies is a really good step in that direction, but also just being transparent as well. So pre-registration ensures hypotheses are determined before running analyses. Pre-registration separates hypothesis generating exploratory from hypothesis testing confirmatory research. And you may hear this term called harking or p-hacking as well. So harking is hypothesizing after the results are known, and p-hacking is where researchers do analyses with all these different variables. They see which is statistically significant, and they try to articulate a story out using those statistically significant findings. What I often see is that in any case, when it comes to this, it doesn't lead to the thinking required to generate new questions. If you p-hack, you never know if it's related to artifacts in the data, if it's really driven by, say, a biological mechanism or framework that's driving the process. And so the scientific process is there for a reason. If you follow that process transparently and honestly, it allows you to say, is there evidence to support my data or not? And in that case, which hypotheses do I pursue next as I generate new questions based on this data and the data of others? So it's really important to consider your hypotheses prior to doing your analyses, and that's where pre-registration comes into play. Replication, there's a reluctance to publish replication studies, and I see that too. And I found a way around it through my research, and you can see that in the example I provided earlier with the hormone replacement therapy and cognition. In part, the first little bit of that study, that analyses, that had been done by other studies. So how was it that I was able to do that and publish it? Well, it's because I did that as my analyses, but I also added an additional analyses on it. So often when I construct a study, I try to have the first step of that study replicate the area of interest that I'm looking at, or the variables of interest of the research that's there, look at the similarities or differences, then progress with pushing the envelope with new research. And I find that finds the balance of allowing me to contribute to replication research whilst also actually contributing to novel research as well. And when it comes to reliability, just how reliable are findings in psychology? Open Science Collaboration looked at 100 studies replicated. The replicated effect sizes were half the size of those reported in the original studies. 36% of findings are significant in the replications compared to 97% reported in the papers. It's massive, massive change in what we see. The idea in science is that the methods is a recipe book. If someone repeats it, they should get the same findings, and that was not the case. So some of the findings that didn't replicate, people are more likely to cheat after they read a passage informing them that their actions are determined and thus they don't have free will. These are the ones that didn't replicate. People are less severe and make less severe moral judgments when they just wash their hands. And partnered women are more attracted to single men when they're ovulating. So these are all findings that were published, but they did not replicate. And psychology is a great example of many of the great stories we know in psychology fail this replication. As you may have heard, the marshmallow test. So the marshmallow test was one in which they asked children to sit with a marshmallow, and they said to the child, you can have the marshmallow now, or if you don't eat it and you wait, when I come back, if I see that you haven't eaten that marshmallow, I'll give you another. And it was really a measure of delayed gratification. And what they found is that in students or children who were able to delay their gratification and not eat the marshmallow, they were able to have greater academic outcomes when they were 15 years of age, achievement at 15. And what was interesting is this follow-up study. So all children in the initial studies were recruited from Stanford University's nursery school. So it was academics with their children who were put into the nursery school. And those were the children who were used. And so they, in a follow-up study, replication study, they said, well, let's control for some confounding variables, right? As we've learned in multiple linear regression analysis. Could this relationship depend on, could this relationship be influenced by other variables, and should we control for them? And so follow-up replication studies revealed socioeconomic status of children explain the variance in achievement at 15 much more than the marshmallow test results. And so in fact, the results that you see could be largely attributed to the socioeconomic status of the child rather than whether or not they were able to delay their gratification. And so this is one of many studies that in psychology that doesn't meet the replication threshold for research. And then so we see this, it's rampant everywhere. So what are the take-home messages? Try to design high-powered studies or consider the use of secondary data sets. That's becoming more and more common. It minimizes the burden of research on participants, allows research to be aggregated, and allows research to be done in collaboration with researchers all around the world. If there's a novel finding, replicate it first. And my recommendation until the research ecosystem changes to be one where it allows for replication studies to be published, I would recommend embedding a replication study as the first part of your study and then building on it. Always report effect sizes, ideally with the confidence intervals that surround them. It's critical and really, really important to do for transparency and ensuring that we understand what the effects mean. And saying that, that's it for today. And that's it for the course and the content in this course. The rest of the next lecture that we do is going to be a summary and a wrap up of everything. But you've finished the content of the course, so well done. Hopefully that was a interesting lecture and really gives you food for thought when you think about the research that you're doing and make you reflect on what type of researcher do you want to be. And I think there's some important questions there and important tools that you learn in this lecture that allow you to critically analyze research, critically think about research, and also critically think about the researcher that you want to be and what the impact has. Because every piece of research you do has an impact, and the even small scale, the attitudes, behaviors that you apply to your research, they magnify on a large scale. So it's good to embed those good practices now, so of ethics, academic integrity, responsibility, so that as you progress in your career, they're ingrained and second nature. Saying that, have a lovely day, lovely week. I'll see you in the next lecture.